It's okay. Is there any question about anything we talked last time? I think there's one up, and it takes a few seconds. Okay, so let's start today's class. What we saw last time was the definition of the class coNP. We basically gave a general definition of how to take a class, we call it even X, and turn it into another class. We called it coX. And the definition was that we take every language in this class, we take the complement, we put all of them together. And the important point was that this is not the complement in the sense of set theory. In fact, for the class of polynomial time algorithms, we saw that the cooperation applied to this class gives the same class. And when we look at the main classes that we defined so far, the common belief is that the picture is something like this. That here we have MP, here we have P, coNP, and in the middle we have P. We saw last time why the class P is in fact in the intersection of NP and coNP, and why the picture is drawn like this, because we have problems here which are NP complete, and we don't know how to solve them in polynomial time. We don't know how to show them to be in coNP. So basically, as far as we know, they're out of P and coNP. We have also problems here which are actually coNP complete. And we saw that basically coNP completeness was closely related to NP completeness. If you take an NP complete problem, the complement is actually coNP complete. This is true for not just NP coNP, it would be true for if we had like a class X, we take a complete problem for class X, we move to coX, the complement of that language would be complete for coX. So there is a symmetry. The symmetry just follows from definition. And I think Saba asked last time whether there are, so two questions. One was whether there are things actually between NP complete and P. So are there things here? And I told you that this is a theorem that we are not going to cover. That part is still true, but I gave the name of the person who proved the theorem wrong. I told you this is Blum's theorem. However, the chapter 3 in fact covers this theorem. If you're interested, you can read it. It's Latner's theorem. It's in the chapter that we're going to go over today, but we're not going to go over this theorem. This is a beautiful theorem, but to give you a high level of how I'm choosing the topics that we're covering, there has been a wave of investigation about very, very subtle issues about the definition of the Turing machine, definition of NP completeness, all these things at the beginning of the time where computational complexity started, like 60s, 70s. However, after like 40, 50 years, some contributions of this theory have shown to be more important than the other ones. Like some parts of this theory still carries on to cryptography. Like if you want to do cryptography, still we need to understand part of the complexity theory, which kind of historically shows which ideas or which theorems are deeper or more useful. So we have in mind like the applications of complexity when we go over the topics. This is a beautiful theorem, but as far as I know, it just doesn't give us anything more. It's still the idea. The idea is interesting, but we will see similar ideas with different theorems. So the answer is yes, but there are things here. However, note that this is a conditional answer, because as far as we know, P could be equal to NP, and by conditional I mean assuming that P is different from NP, then there are things that in between. And also there was a question about whether there are things here, and I told you that we had a candidate till a couple of years ago, like factoring was a candidate that it was here. However, at the moment we don't have the factoring. I did a little research, I didn't find any other problem that we know provably to be in coNP intersect NP, but so far out of P. However, under some conjectures that people believe, for example, I can tell you exactly what the conjecture is. Under the conjecture that satisfiability problem is not just hard in the sense of polynomial time, but it's hard even in the sense of sub-exponential time. So there is a conjecture saying that if you want to solve 3-SAT, you really need to run in time exponential time, not just super polynomial, but in fact exponential. There is a conjecture which is very close to that, which is believable, highly believable. Under that conjecture, we can construct languages which are out of P, but they're in NP intersect coNP. So the common belief is that here there are problems that they exist out of P. So that's why we draw the picture like this. And now you get a sense of what do we mean by common belief. Even though, as far as we know, they could all be the same sets, but we want to understand what's the most likely case, and we consider the fact that, for example, for NP complete problems, there is no algorithm so far, so most likely they're going to be here. For future, we want people like you to actually prove it. We have had little progress in the last. This is a very young theory compared to other. So if you compare computational complexity to other fields of mathematics like group theory, analysis, it's very, very young. It's like basically started in 60s or 70s. And as a research point of view, it makes it more interesting because very basic problems are still open. You might become one of the most important guys in the history if you solve one of these problems, because these are very basic questions that are mathematically also deep, but after 40 years we haven't been able to solve them so far. So this is the common belief about what the picture is. And something that I want to tell you very briefly is that we define the class NP coNP based on just saying that, okay, how this operation co-applies to any class. However, it's good to keep in mind what is the direct definition of coNP. And I just want to briefly tell you that if you look at the definition of NP, how did we define it? We defined it using a witness system. We say that the language L belongs to class NP if the following holds. There exists some verifier that we called it, say, verifier for L, such that X belongs to L. There exists this verifier which is polynomial time. And also there exists this polynomial bound, say P. So some bound over the length of the witness such that X belongs to L if and only if, here is the keyboard, there exists some witness of length, say Pn, and n is the length of X, such that V accepts X and W. V sub L. So one thing I want to emphasize is that this definition doesn't matter whether we say here accepts or rejects. If I here write rejects, it's the same definition. Why? Because we can always flip the output. If it says accept or reject, we can always change it, and we end up with a different verifier that does it in a more natural way. So here the accept or reject is not the crucial point. However, this quantifier that says there exists, this is something important. That's the heart of the definition of this class NP, and we apply it only when X is in L. Now, if we want to just use this particular definition and see what would be the definition of the complement of L, now we want to see what is the definition of this, which we already know it's a language in coNP. What we can do is that, just apply the logical rules to this definition to see what definition we get. The definition of L was that there exists this verifier, blah blah. Now we already know that this verifier exists. We want to see when something actually is now A. So we have the same thing. So we want to give a definition for L bar. We already know that when L bar is in coNP, we have to have that L was in NP already. So we already know that there exists this very same thing. There exists a verifier. There exists a polynomial P. Everything the same. Now, what happens? What is the change? Now X belongs to L bar if and only if I have to write something which means that X does not belong to L. Yeah. That's the only thing. That's what I want to write here. That would be the definition of L bar. And then I would just have to go over the logical statement here. When do I put X in L? I put it whenever there exists a witness. Now the negation of that statement is that just pure negation of logical sense is that for every W of this length, verifier rejects. So it's just that I'm not doing anything smart. I'm just negating the definition in this sense to get the complement language. And again, I want to emphasize that I can write here reject or accept. It's going to be the same definition. That's why. So this is the definition we got pure logically. However, the tradition is that here we write accept as well. And I hope you are all convinced that writing here accept or reject doesn't change the definition. I could write accept or reject here as well. But what is important here is the quantifier change. So now we have this for all something happens. And this is the key word that whenever you see a problem, if you want to quickly judge whether there's an NP problem or quick problem, you have to see when you're describing the problem for yourself, is the quantifier existential or universal? If I ask you, what is the complexity of the problem tautology? Tautology is that I only put things in my language if the circuit or 3-stat formula is always satisfiable. If it's always satisfiable, then it's coNP. But if I said there exists an assignment that makes it true, or there exists an assignment that makes it false, they both fall into NP. It doesn't matter if it's true or false. The point is this quantified. So this is something that is good to keep in mind about the definition of the class. Something else that I went very quickly toward the end of last time was this alternative definition of the class NP that I want to describe it a little more formally because we need it for we need this definition for future as well. So the other more traditional definition of the class NP is through this notion of non-deterministic Turing machine. We defined non-deterministic Turing machine before. I quickly recall the definition. The definition is that a non-deterministic Turing machine is something close to the way we define non-deterministic automata. You have seen it in the theory of computation course. That it's not clear what is the next step of the machine, and we defined it by saying that there exist two, or at least two, transition functions. Delta 1, delta 2. And in fact, it is equivalent. You can see in the assignments that I could write 3, 4, it doesn't matter. They all turn out to be the same definitions. What is important is that there is more than one way to proceed in every step. So the machine, at any moment, it looks at the memory, it's in one state. It wants to decide about what to write in that memory cell and which state it wants to move into. And the way it decides how to change the state of the machine is based on one out of two possibilities, delta 1, delta 2. And the definition of alternative definition of L being in NP is that there exists a non-deterministic Turing machine. I don't want to use the previously we defined it with a verifier. That's the more intuitive way of defining it, more useful for our previous purposes. This time, non-deterministic Turing machine, let's call it that's just M, such that, first of all, this is again a polynomial time, because the notion of time, you can define it the same as before. The time now bounds the number of steps of the Turing machine. Even if the Turing machine is non-deterministic, if I say it runs in time t, it means that it would stop after t steps no matter what. So the time is the same as before. We just don't know which branch the machine would choose to go. It has choices every step. That's the only difference. So there is a non-deterministic Turing machine of polynomial time such that X belongs to L if and only if ML accepts and I wrote accepting quote unquote because the notion of acceptance, so the machine, suppose the machine always outputs 0 or 1 after polynomial steps, and 1 means accepting, but here the machine could go in different branches. So what do I mean by accept? By accept I mean that there exists a way that ML accepts. So you see that already the definition of acceptance is somehow based on this existential quantifier, which should remind you of the definition of the class NP already. Well, this is a definition of its own. It says it accepts, just defining it as there exists a way that the Turing machine. So one out of the, suppose the Turing machine has 2 choices in every step and runs in time t, then the number of possibilities is like 2 to the n. So at least one out of these 2 to the n branches that the machine could choose would accept this. And again, whether this whether the machine at the very end outputs 0 or 1 doesn't matter. We can always change the 0 1. But the key point here is this: so there exists a path that when we look at the ending result, we see some special answer. Say, okay, accept or star or something that we know the machine is happy, X is good. So this is the definition of non-deterministic Turing machine. We can define directly using this definition. We can define coNP, the class coNP. So I'm going to tell you in next slide a little more carefully why this definition is equivalent to our definition of using witness. That's something we went over quickly. But this definition, if you believe me that this is the same definition as using witness, and if you say, okay, this is the definition of class NP, we can use this machine directly to define the class coNP. So can you tell me how would be the definition of coNP? So when do I say L belongs to coNP using the notion of non-deterministic Turing machine?
The non-deterministic Turing machine would reject in all of its branches. There's no branch for which it accepts.
Exactly. So the only thing we have to do is just change the definition by changing the quantifier, basically, saying that there exists a non-deterministic Turing machine ML such that X is in L. Now let's call it like this way. If for all branches of ML okay, so this is just keep so the notion of non-deterministic Turing machine, we would see it later on. It's for some reasons it's interesting on its own. For some applications that we'll see in next sessions, we need the notion. The notion is very easy, but keep it in mind till we go there. So why the definitions are equivalent? I want to say that definition 1 based on witness, so witness-based definition is equivalent to definition 2 using non-deterministic Turing machine. So I mean the definition of class NP. So very quickly I want to see if you all can see why these two definitions are the same. So we just have to study in two directions. First, we assume that the language is in NP based on a witness relation, and we want to see why it has a non-deterministic Turing machine. And then we assume that it has a non-deterministic Turing machine. We want to construct a verification process for it. So suppose L belongs to NP version 1, and by version 1 I mean definition based on witness. So why can we say that L belongs to NP where definition is based on non-deterministic Turing machine? So why is it the case? Can you tell me? So always it's good to start with the definition. You know, in a theorem you want to prove any assignment, any research question. Let's start with the assumptions very formally. What is the exact definition of this? When L belongs to NP based on the witness relation, we already know that there exists a verification process BL and such that X belongs to L if and only if there exists a witness of certain length, of at most a polynomial length, such that X and witness together are accepted. Now we want to say that L belongs to NP under a different definition, and the different definition requires a non-deterministic Turing machine. So we have to construct that non-deterministic Turing machine. We have to do it in a way that the non-deterministic Turing machine would somehow accept everything that we want it to accept, which means that it accepts only if and only if the witness exists. So any suggestion?
The Turing machine could sort of act as your verifier, and then it could try all the witnesses, or it could try all of them, and the witness is the one that would cause it to accept. So that would kind of be like this sequence of steps in that branch that led it to.
So what you're saying is that what we did not know here is the witness. The witness here is like, suppose the witness has like length k. Then the point is that there is a space of 2 to the k witnesses that we want to know whether there exists any of them which makes us accept. That's the thing we don't know. We don't know the witness. In the definition of non-deterministic Turing machine, suppose the Turing machine has k steps. Then there is also an uncertainty there as well, that in k steps you don't know where the Turing machine would go, and you would accept the input if one of those branches makes you happy. One of those branches reaches accept. So what we can do is very intuitive. We would somehow simulate the job of finding the witness through non-determinism, which, if you think about it, at first it might sound like irrelevant, but it's actually very, very easy to do this job. Let's see how we do it. So we have this tape. At the beginning, suppose you have only X on the tape, and you want to construct a non-deterministic Turing machine that would accept this X if and only if there exists a witness that the verification process would accept. Is it clear what we're doing? Everybody sees why we are constructing this non-deterministic Turing machine. So here, suppose that the tape would write, we would write the witness in tape following X. So suppose this is the W of length K. So basically what we want to do is that through non-determinism, we want to guess the witness. which is suppose of length k, what we can do is this. More or less, this is like a pseudocode. So I have to give you the code of the Turing machine, non-deterministic Turing machine. As I told you before, I won't give you like details, but it should be detailed enough so that you can convince it can be implemented. So what we do is that we read input. After reading input, all we do is that the Turing machine, non-deterministic Turing machine, would go into a special state, let's call it, by reading input, I mean just move the header toward end of the input, go into state Q. Suppose the state Q is like a special state that we go into Q. After that, we would either go into a state Q1 or Q2, and depending on which state we go, we write a different thing on the tape. So what we are doing is that we want to somehow use non-determinism to generate the witness. And non-deterministic Turing machine has this extra power or extra power just put in its definition that it might go into different branches, and we don't know which one it goes. And just with the same, with this very power that it has, we can generate the witness non-deterministically. So we would do this. We'd say then for. I mean, I'm writing into the for loop, but you can write it just with the Turing machine's definition. For k steps. So there are details that I'm hiding here. So for example, we need a counter of counting the k steps. We can have part of the Turing machine allocated to that tape, and every time we have to go back and increase it. I'm basically writing the pseudocode in the language of, say, C or Java, or something that we can understand easily. But the non-deterministic Turing machine, you can see that there is a very similar definition. You can have it on RAM model. So the only point that we have to have in non-deterministic Turing machine or any other model is that you have choice in how to go to the next step. And you can see that all these models are equivalent. You can translate them back and forth. For k steps, generate wi non-deterministically. And by generating non-deterministically, I mean that when you go to a state 0, Q or Q0 or Q1, you would write 0 or 1 on the tape somewhere. And then in every step, you have the choice to go which direction. At the end, k steps W is generated, and then just run over. We just run the verifier over this witness that we generated. So basically what we are doing is that we say non-determinism means that the machine can go into left or right. And we can directly use this feature as saying if the machine goes left, I would write 0. If it goes right, I would write 1. I can translate that feature into writing something over the tape, where after k steps of writing, you have a string of length k, where all possible answers could have been written there. Because there are 2 to the k possible ways after k steps of non-determinism, and there are 2 to k strings, and all of them have a chance of being generated. And after you generate this string non-deterministically, all you do is to verify it. And as you can see, if there exists a witness that is acceptable, it means there exists a branch that I make. So don't forget that when I say just run this verifier, I'm doing something deterministically, yes? Non-deterministic Turing machine has the choice of going into 2 different states. It doesn't mean that they have to be different for sure. It could be different, it could be the same. Namely, what we are saying is that non-deterministic Turing machine could be also just a simple deterministic Turing machine. So it's a more general definition. It's not incomparable, it's comparable. It has the choice of going into 2 different branches, but those 2 branches might as well just be the same. which means that we can run any deterministic algorithm as well through a non-deterministic Turing machine. So non-deterministic Turing machine, in a sense, is more powerful. So therefore, this run verification at the end is something we can do. It's not out of the power of an deterministic Turing machine. And now you can see that this Turing machine or algorithm pseudocode has 2 to the k possibilities at the end, based on which choices it makes in every step. And one of these 2 to the k possibilities would give us accept if and only if there exists a witness W that makes this verification process accept. You all see that? Just using non-determinism to generate the witness. So it shows what it shows. That shows basically show that the definition MP1 is a subset of MP2. If whatever we use under definition of witness, we could achieve it under the definition using non-deterministic Turing machine. And we want to claim that MP2 is also a subset of MP1. So I won't write that part. Can you just tell me? So if there exists a non-deterministic Turing machine for some language L, can you tell me what is a witness verification process for it? So is the question clear to everybody? So I have a language, it falls into NP under the second definition, which means that there exists a non-deterministic Turing machine that accepts or generates this language according to the definition of non-deterministic Turing machine. And we want to define a verification process that basically gives us the very same language. Yes.
Just the list of steps that the non-deterministic Turing machine takes.
It works, yeah. So what would be, suppose you know the code of the non-deterministic Turing machine. I claim that this non-deterministic Turing machine would accept the input X. How can I justify my claim for you? All I have to do is to tell you which branches the Turing machine should take. There are maybe at most 2 to the n possibilities. If the Turing machine runs in time n, or k 2 to the k possibilities. The issue is that there are 2 to the k possibilities and we don't know which one of them leads to accept. However, if I claim that there exists a branch, and if I give you the branch, you can just run the Turing machine over that branch and see that it actually does achieve the accept. So this is also easy, saying that witness, I will just write it. Witness is the choice of all I have to say is that basically the witness that something belongs to the language could as well one way of generating witnesses and verifying witnesses could be that the witness is just the choices the machine makes. And if I give you those choices in a list, suppose the Turing machine either goes left or right in every step. For time k, I will just give you a string of 0, 1 of length k. And 0 means that machine went to the smaller state. Whenever it has a choice between 2 different states, look at those states, which number is the smaller or the other one. If I give you 0 means that the machine wants to go to the smaller one, 1 means that it goes to the larger one. And if I give you a string of length k, it basically defines k steps of non-deterministic Turing machine. And you just, if I give you the sequence of choices, then the Turing machine becomes deterministic. You can just run it. You're using universal Turing machine and you would. Okay, so you can see this theorem proved in the book also. So if you basically didn't follow everything closely, you can ask me now, or if you thought you understood it and after class you had doubts, you can look at the book or you can come to the office hour. But the most important thing is not this equivalence, I mean, it's good to keep in mind that these two definitions are the same. It's good to understand it for sure. The main thing is the definition of this non-deterministic Turing machine, that we might use it later on. And the definition of non-deterministic Turing machine has this quantifier somehow built into it as part of the definition of what it means for a Turing machine to accept something, which is the non-intuitive part of the machine. It's not a natural way of doing computation. Okay. So non-deterministic Turing machine, we defined it. It turns out the definition of NP under this definition and our previous definition are the same. These are basically things that we wanted to know. I wanted to wrap up before leaving the NP completeness chapter. For the next chapter, we will see one of the basic theorems of complexity theory that some of you might have seen it in the class, theory of computations. How many of you have seen the time hierarchy theorem in theory of computation class? So it's proved in the grad course but not undergrad. Is it true? Okay. We will go over the theorem. So the grad students, it might repeat for you, but I will prove the theorem basically from scratch. But the part that probably you haven't seen, none of you have seen in the theory of computation, is that we will prove this theorem and then we will ask whether the same techniques that we use to prove this theorem can be used to prove P different from NP. And there is some interesting ideas of why this technique cannot be applied to P versus NP. So those are things that would be new to you probably. But what is the theorem? The theorem says, well, we have a very, very basic intuition that if you let me run in time, say n to the 10, I can solve more problems, compared to the case that I run in time n to the 2. So in the algorithm course, you can see that if you solve a problem in time n to the t, and then you do a lot of optimizations and you run it in time like n log n, but it seems no way to be no way to do it like, say, linear time n. So there seems to be some inherent limitations to every problem. I optimize the algorithms running time, I end up with n to the 5, I cannot do it into the 4. But there are other problems that I solve into the 4. So it means that the more you have time, more and more problems could be solved. So one unusual thing that could happen is that, well, everything either doesn't have any polynomial time algorithm, or we can solve them in n to the 100. So that's a possibility, but it's kind of counterintuitive, saying that, well, there might be a problem, most probably there is a problem that I can solve it in n to the 200, but not n to the 100. The time hierarchy theorem, basically any hierarchy theorem, not just time. It could be, we will see other versions of hierarchy theorems. Time is a resource, yes, so this is, as you recall, in this course we want to understand how useful different resources are for computation. We want to know how useful time is. How do we formalize this question of being useful? Useful here, this is a way to formalize this intuition, saying that time is useful in the sense that the more time you have, the more problems we can solve. So time somehow is a useful resource. And then we will prove these theorems through a technique. This technique is called diagonalization. You will see it. You have actually seen already some theorem that is proved using this. I'll remind you about that, and then you will see what are the limits of this technique. Why we cannot use this technique to do something. Okay. So the time hierarchy theorem, the informal version of it, I already told you. The theorem says basically in any reasonable model of computation. Here we focus on Turing machine, but you can prove it for RAM model. After you see the proof, you can prove it basically. When someone defines a model for you, you can come up with your own proof using the same technique that in that model of computation, the time hierarchy theorem holds. So the intuition is kind of independent of the model, but so we will prove it for Turing machine. The theorem says that the more time we have, the more computational power we have, so we can solve more problems. We want to formalize this theorem for Turing machine case. For a formal theorem, we would say, well, let's call d time Tn, it's a complexity class. I want to somehow write a theorem that formalizes what I said above. Deterministic time Tn, let's call it the class of all languages that we can solve them in time Tn deterministically. So this D is to emphasize that we are not talking about non-deterministic Turing machine. It's a deterministic. So the class, basically the class P, a formal definition of class P would be the union of D time n to the k for all k in natural numbers. So basically it's a subset of class P, but I'm going step by step quantifying more over the time. So the theorem says that, for example, the time, this is not the most general statement of this theorem. If you look at the book, the book writes a theorem that implies this. The book wants to basically compare deterministic time of some time, like say n to the k plus epsilon also, to the deterministic time k. But for simplicity, what we will prove is that the class the deterministic time n to the k plus 1 includes more languages compared to deterministic n to the k. So is the statement of the theorem, first of all, you all agree that do you all agree that this is the case? The right hand side is a subset of the left hand side, yeah? Because if I can solve the problem in time to the n to the k, that's a smaller number than n to the k plus 1. So I have already solved it in time n to the k plus 1 as well. So by definition, the right hand side is a potentially smaller set. What the theorem says is that they are not equal. Basically, the left side is a larger set. So everybody is comfortable with the definition of deterministic time n to the k and this theorem? The definition of the theorem is clear to everybody? Okay. Now we want to prove it. So in fact, before proving a theorem, I want to tell you that just the way you define deterministic time Tn, we could as well define non-deterministic time. Non-deterministic time. Let's just not write even D. Non-deterministic time Tn. So I could define a class non-deterministic time T very similarly by basically combining the notion of non-deterministic Turing machine with this definition. The definition would be that the language L belongs in this class if there exists a non-deterministic Turing machine of time complexity T that accepts L. So why did I define that? Well, there is a theorem, very similar theorem corresponding to this, that actually shows that non-deterministic time n to the k plus 1 is also more powerful than non-deterministic time n to the k. Okay, so this theorem is true, and the proof is very, very beautiful and elegant. However, we won't cover it in the class because this is something that we will. So the versions of the theorem, the first theorem, that we will see in the future uses the same proof. So this is something we definitely have to understand because of its applications and similar theorems in nature that use the same proof. This one is true as well, but I personally do not think that is as important, even though the proof is very beautiful. So for whoever is interested in this theorem, I definitely encourage you to read the proof of this theorem from the book. After we see the proof of this theorem, you will see that the proof somehow does not directly extend to this. However, with a little bit of tricks, some of them are very smart, you can prove this theorem as well. So can anyone tell me what does this theorem, the second that we're not proving. What does it mean when we use the definition of NP using witness? I don't want you to say something very precise, but what is roughly speaking going on here? I want to see whether you are basically getting the main message of this theorem for non-deterministic case. For deterministic case, it's pretty clear. Yeah, it just says the problems that you can solve in time into the k plus 1 is a bigger set. Yes. What does it mean here then?
Given more time, we can find languages with longer witnesses.
Given larger witnesses, we can decide more languages. Basically, the main point I want to say is that the time in non-deterministic Turing machine somehow corresponds to the length of the witness when we define the non-deterministic, when we define NP using the witness. I'm not being precise here, but you can make it into a precise theorem that when you are working with witnesses of length n to the 10, the languages in NP that you can define this way is a bigger set compared to the languages that you define with witnesses of length n to the 5. So this is not a completely useless theorem. That's why I wanted to basically translate this theorem into our previous definition of NP. I'm not being formal here because this is not a very precise relation. When we prove the two theorems, the two definitions to be equivalent, we basically had to generate the witness and also run the verifier. So there is more to do it, but you can turn into a formal theorem. What we will prove is this one. We'll prove the first one, but I would definitely suggest whoever is interested in understanding better the proof technique to read it, because the proof is somehow elegant. I think the proof is by Cook, the same person who proved the main theorem that we saw so far. So he's a very smart guy. This one is one of the most beautiful theorems, but unfortunately because of time it might take like half of the session to cover it. We won't. Okay, so now we want to prove the time hierarchy theorem. Is there any question about this theorem or just the statement of this theorem? Let's clarify it before proving it. No question? Okay. So before proving the time hierarchy theorem, I want you all recall something that you have seen before, but I will go very, very quickly, because this theorem that you have seen tells us how to prove the time hierarchy theorem. The technique is the same. Two problems are different, but the idea is the same, and that's why when you use a technique over and over, people give it a name because the technique becomes important, and we want to talk about that technique on its own. The technique is called diagonalization. We will see later on, but let's see first of all what the halting theorem was. Halting theorem says, well, the goal is to construct a language that cannot be decided. The language cannot be solved in any time, not just polynomial time. There is no algorithm that decides the language. So there are different versions of the halting theorem. I will just the version that I prefer, like whoever might write it in their own way. So let's call HL a language that I write a string M. So I recall that we can encode Turing machines in different ways. Just keep in mind one possible way that we can encode Turing machines. First, for example, by encoding, I mean that first of all you list the states and then you write down the truth, the if then else table of the Turing machine. So just the way we, for example, write it down in the easiest way. Now, if you give me a string, first of all I would try to decode it as a Turing machine. If I cannot decode it as a Turing machine, I'll just put it away. I won't accept it. However, if you could decode it, then I would accept this M. I would put this M inside the language. I would include it if and only if the following happens. If you run the Turing machine M over input, which is also M, so you can run a machine over itself, yeah, because they're both strings. Then, if it halts, I would include it. I would say this is something I prefer to keep it. Otherwise, I would not include it in the language. Okay? So this is the halting language. I claim that this language is not decidable. And so the statement of the theorem is clear, yep? How do I prove it? I do it this way. I say, look at this machine, M bar. I want to construct a particular machine M bar. I say this machine does the following. So first of all, before that, I'm saying assume A solve. So we want to prove that it's not decidable. We start by the counter assumption that actually it is decidable. So we assume that there exists an algorithm A that solves the halting problem. Then we say, okay, look at this particular machine. The machine takes input X, and then if X belongs to the halting language, then fall into loop. If X is not in halting language, then halt. So what this machine does is that it gets an input X, and it wants to know whether this input X belongs to this language, halting language, or not. Okay? And we are assuming that we can decide this because we already assume that this halting language is something we can solve in some time. And what I'm doing is that I'm basically defining another language, or by language I mean I'm defining a process that if we give it an X, it would somehow either fall into loop or would halt. So is the code of this machine M bar, is it clear? Let's not just call it M bar, just M, because we called it, yeah. So I first assumed that the algorithm A solves the halting problem, and then I constructed the Turing machine, I called it M. And all it does is that it takes input X, depending on whether X belongs to the halting language or not, it would fall into a loop, or it would not fall into a loop, which is something easy to do. Like falling into loop is easy, you just repeat a state into itself, and it goes forever. So okay, what is the problem? What is the contradiction now? The contradiction is that M, the machine M, if you execute M over itself, it's not clear what happens. So I say, what happens if you run M over M? It's clear what it means. Yeah, M. You write down the code of M. M has a code. Yeah, it has a description of the Turing machine, whose description actually depends on the description of A, because it's running A as a subroutine somehow. What we're saying is that if you run this machine over itself, then there are two cases. Yeah. Either M halts over M, or M does not halt. I want to say that in both cases, I want to say that this implies the other and this implies this one. Basically, you cannot see, none of them can happen, because if this happens, it implies the opposite. That would be contradiction, yeah? So why is it the case that it implies? So if M halts over M, what's the problem in this case? So if halts M over N, let's forget about everything in the middle. If M halts over N, Does it mean that M also belongs to the halting language? It's just a definition, yeah? It says whenever something halts on itself, I will put it in this language. Okay, if M belongs to the halting language, now go over the code of M. The code of M tells you if you give me X as input, which in particular case is just M itself, what it does is that it first verifies whether this belongs to the halting language or not, which in our case, as we saw, it does. Yeah, everybody agrees? And because it does belong to the language, it falls into the loop. So it does not halt. So we started by definition and we concluded that it did not halt. So basically, step by step, M belongs to halting language, and then M does not. And the other way, if M does not halt on M, again, very similar argument. If M does not halt on M, it would not be in the, just opposite, it would not be in the halting language. You agree? Just definition. And because it's not in the halting language, now I go over the code of M. It takes X as input, which in particular case is M itself. Now, when you go over this if then else case, this X, particular X, which is M itself, would not be in a halting language, and then we would halt. So you conclude that M does not belong to halting language, therefore M halts. So you see that in both cases we get a conclusion, we get a contradiction, because depending on which case we are, depending on whether M actually belongs to the halting language or not, what is happening is that when you run it on itself, it somehow finds the answer and does the opposite, which is a contradiction. So if this proof is clear, I mean, you more or less should have seen the same kind of proof in your theory of computation. I just reviewed the proof. This is a full review, so if you didn't follow it, you can read the notes later on. I want to apply the same idea to prove the time hierarchy theorem, which is, to me, is a more interesting theorem than this, because in this course we don't care about something being computable or not. We care about the actual running time, the actual resources that we use. But we want to apply the same ideas. I want to see if I want to tell you how do we run the code of A inside M. Like, what is the theorem that lets us do this? Like, we had a theorem in this class that if you have a Turing machine, another Turing machine can run it, and we call it universal Turing machine. So basically, at this step, I'm being not precise. If I want to be precise, the machine M is basically using the universal Turing machine to run the code of A. Because the Turing machine M, the way I defined it, it runs the algorithm A, which I'm assuming it exists, and then somehow after that does some decisions. But I wanted to remind you that the machinery that we are going to use also for the time hierarchy theorem is the universal Turing machine. Okay, so is this clear now, the proof of the halting theorem? The main message is that you have an algorithm that somehow wants to contradict itself using the universal Turing machine. Now we want to prove the time hierarchy theorem. The theorem now, without the definition, is very simple. We just say we want to prove that the deterministic time n to the k plus 1 is a larger class, complexity class, compared to just deterministic time n to the k. Okay? And you all recall that I'm writing a theorem that we saw before. We didn't see the proof of it, but we're going to use it. So you could see the proof in the book. The proof is not that important because this particular bound that the proof achieves, we don't really care about this bound. But we're going to use it, so the theorem is correct. Why not using it? We could easily prove something like with n to the 10, but in log t is true. So what the theorem says that there exists a universal Turing machine that if you give to this Turing machine a code of a machine M and some input X, then the machine can simulate T steps of the execution of M over X in a time which is kind of close, which is like T log T. So this is the theorem that says, the theorem basically says universal Turing machine exists, and it's a more quantitative version of saying that it exists. It says basically what is the overhead of the Turing machine's running time when you move to the universal case. The universal case somehow simulates the execution for you. It takes a little more time than before, but this little more time we know how much more it is. So if it was T, it's like T log T. Now, what do you suggest? Suppose for simplicity, I want to prove that n to the 2 deterministic time n to the 2. I want to say that it's a bigger class compared to deterministic time, just like 10n. Basically linear time. I want to say that if you have, n squared time, you can solve more problems than if you want to just run in linear time. So if you want to use the ideas from the halting theorem to prove something like that, what would you suggest? So I want to construct a language. So keep in mind what the definition of this, not definition, the basic implication of this theorem. What it says is that there exists a language that we can solve it in n squared time, but we cannot solve it in linear time. So the general idea behind how to prove it, it should be that we should construct a language. Along the time that we are constructing this language, we somehow should show that this language can be solved in n squared time. However, using the same kind of contradictions that we saw in the halting theorem, we should be able to argue that this language cannot be solved in, say, time n. So at a high level, what we should do is that the definition of the language itself should somehow let us prove that the language cannot be decided in time n. And this would be the similarity to the halting theorem. And the definition itself should somehow contradict itself if you could solve it in time n. So after we do it, you will see that the proof is not complicated, but I want to just tell you where the proof comes from, like not just like a magic to see it. The proof is step by step like this. We want to construct a language L that belongs to deterministic time n squared, but L does not belong to deterministic time n. Well, n is deterministic time n for Turing machine is basically meaningless, because in time n you just have the time to read the input. That's why I wrote 10n. But the main message is that you could apply the same theorem for any n to the k and any n to the k plus 1. So even though that's meaningless, forgive me. Okay, any suggestion? When I want to define this language, basically I have to tell you, if you give me x, when do you put x inside the language L, and when do you put it outside the language? I have to tell you that. If I tell you that, then I have defined the language. Yeah. So I want to define the language in a way that somehow by the definition of the language, it's clear that you cannot solve it in time n. Any suggestion? Not clear, but following the ideas, somehow we should be able to prove something like that. So I would say So the same technique as before. We run x over itself. We interpret x as a Turing machine. We run it over itself for time, say, n to the 1.5. This time is just something between, n and n squared, something in between. I want to draw a line where, I can separate these two classes. I'm choosing a running time in between. And what I'm doing is saying, okay, give me some x. I want to decide whether I would put x inside this language or put it outside the language. What I'm going to do is that I would run x over itself for, say, time n to the 1.5. And then, what do you suggest now? If x accepts itself, then we would reject. By reject means that I would put x out of L, which means that x does not belong to L. If x rejects, or otherwise, basically, if it doesn't accept, I interpret it as reject. So what's going on? I take an input, I run the input over itself, and I do the opposite. So if it accepts itself, I reject. If it rejects, I accept. It's close to what we did in the halting problem. Yeah, in the halting problem, we run over itself, and we decided the opposite. We are doing very similar case here. The key difference here is that we run it over a particular number of steps. For the Turing machine case, we didn't care about the number of steps. We basically said we run it till it halts. It could be like million. It could be like much larger than this, because we basically run it forever. We wanted to know whether it halts or not. Here we run it for a specific number of steps, n to the 1.5, which basically is just a function between those two numbers. And what we do is that we decide the opposite as before. Now, first of all, the easy part. I'm just defining this language. What is the running time? If I want to solve this language, so if I want to basically decide whether x belongs to this language or not, how much time do I need to decide this? So is the definition of the class clear, how I'm defining it? So now that the definition of the class clear, suppose you want to implement an algorithm that decides this language. What would be the running time of your algorithm? So how do you do it? What is the tool that you would use? What is the main tool you will use to basically solve this language? Any suggestion? Yes, we just need a universal Turing machine, because this class, all we need is to run x over itself. And then we do it for a number of steps, and then we know the answer. Yeah? So we can decide, so L belongs to, what is the running time then? So if we call n to the 1.5 like t, we can decide this in time t log t. Yep, this is the overhead, because we won't solve it in time t exactly, because we need to run this algorithm x over itself. We need to do it through the code of the universal Turing machine. The universal Turing machine would take a little longer time, because it's an interpreter, and the time it takes is like t log t. Now this little t is actually n to the 1.5. You can see that this is still smaller than n to the 2. This is like, because the logarithm of n to the 1.5 is still smaller than any polynomial. Logarithm is much smaller than polynomial. Let me write it. So definitely the number is smaller than 2. What does it mean? What does it mean? It means that the language L actually belongs to deterministic time and n squared. And our goal was to construct something that is actually solvable in time n squared, but not solvable in linear time, yes? So don't forget what the goal was. What we did was that we defined a language similar to the halting problem, basically by running every input on itself and deciding the opposite way. But the time that we chose here, the number of steps that we chose, how many steps do we run the program on itself, the time was small enough so that we could do everything in n squared. So you would see that, if I choose here like n to the 3, I wouldn't know how to conclude that the language belongs to n squared. Because if this time was n to the 3, then I needed n to the 3 steps to run x over itself, and it would take time more than n squared. So this is something that I chose carefully to be smaller than n to the 2, and that's why L belongs to deterministic time n squared. Okay. So this is clear to everybody? Now the other side. I want to conclude why L does not belong. I want to claim that L does not belong to deterministic time 10n. Why is it the case? Similar to the halting problem, you have to assume that actually it is in this language and try to get a contradiction. So that's why I went over the previous proof, because there is a similarity with yes, go ahead.
Going back to what you did earlier, does it matter if we pair x with projection?
Can you say louder, a little louder?
For the two cases you have, for if x accepts x or if x rejects x?
In how many steps? Yeah.
Does it matter if we pair exception with projection?
So don't forget that the algorithm, when you run it for a number of steps, it might accept, it might reject, it might be in the middle of computation.
Yeah.
However, because of the way that I decided these two cases, I somehow say if it accepts, I would reject, and if it does anything else, I would accept. So I could write 3 cases, I just wrote 2.
No, I mean, does it matter? Like you say, if x accepts x, then we accept x not.
If x accepts x, then we reject x.
Yeah, but if we accept steps, is that?
So we have to see how the proof goes. The proof that I'm giving you, it's very, very important that we reject here. Actually, if you go to the previous slide, for the case of halting problem, it was very important that whenever x belongs to the halting language, we somehow did the opposite. We fell into loop. So the halting language means that something does halt. We did the opposite. We fell in loop. And if it did not belong to the halting language, we did halt. It was crucial that we did the opposite, because that was exactly how we got the contradiction at the end. At the end, we said if the n, some program n that we defined, halts over itself, then we concluded that it belongs to the language, then we concluded that it did not halt on itself. And that was the step because of the way we defined it this way particularly. Otherwise we would get no contradiction. So you see why we got the contradiction, because of the trick that we did in this step. And if you go here, that's exactly the similar trick we are doing here. We are saying that if x accepts itself in n to the 1.5 steps, then we would reject it, and vice versa. If it does not accept, which could be reject or something else, you would accept. And then, because of the very same reason as the halting theorem, I want to conclude that L does not belong to time, deterministic time 10n. Can you see why? This is the last part of today's class. So go step by step. Let's assume that L in fact belongs to the time 10n. What does it mean? Just the definition of the class means that there exists a Turing machine that solves L in time 10n, yes? You all agree? I'm just following the definition. There exists some M that solves L in 10n time, in time 10n, yes? M is like a deterministic Turing machine. Now, what would you, I want to get a contradiction, what do you suggest? What, James?
So if you assume that's in L, and you assume that's also in N.
L itself is a language that we are assuming to be in time 10n. L is a language. Yeah. So I didn't understand your sentence. So I defined the language here. I wanted to construct a language L that belongs to this time but not this time. And how I defined the language, I said give me some x, I want to decide whether I want to put x inside L or want to put it outside L. What I did is that I did a little bit of computation over xn itself and did a little bit of thing, and at the end I said reject x basically means that it doesn't put in L, or if it's something else happens I would put it inside L. So this part, these 3 lines are my definition of the class L. How did I define the class L? Yep. Is that clear? Then I said this part. So let me. So here is the definition of L. Here, this is the claim number 1. This is claim number 2. So, at least parse the, let's make sure it's clear what's going on in this slide. First, the goal is to construct something that we can solve in time n squared, but not in time n. We constructed the language here just the way we constructed some language in previous slide to prove the halting theorem. But the main difference here is that we run the input x over itself for a specific number of steps. And that specific number, it shouldn't be too large, it shouldn't be too small. We should choose it between n squared and n. You see why. The fact that this number is smaller than n squared makes this problem rather easy. Because this is n to the 1.5, I can use the universal Turing machine to basically run this code that I just wrote here to decide the language in time n to the 2. So the first part says that this language is not too hard. We can actually solve it in n squared time. The last part that I want to just say and finish the class is that this language, because of the way I defined it, it cannot be solved in time n. Just it would be self-contradictory if I could solve it in time n. And the reason is the following. Why do I say it? We said if we could solve the problem in time 10n, then there exists a Turing machine that actually does the job, because that's the definition of time. Then what happens if you run m over m? If you run m over itself, I want to say that it's not clear whether it should accept or reject. For the same reasons that we got into contradiction for the halting problem. But this time there is more quantitative argument. If you run m over itself, what happens if suppose m accepts itself? Then what is the contradiction?
Then it would be fundamentality, but it would be rejected.
Exactly, it would be this case. So if m accepts itself, then look what happens if x is n. X is n. If x, this input x, was actually n, it's exactly what Nicholas? What yes. Nicholas said is that in this, what we get in this case, because it accepts itself, it means that, first of all, this acceptance happens in 10n steps. It's crucial that the number of steps that m takes is small. So m runs in time n, is a quick program. After n, so if we run the program over itself for n to the 1.5, it is enough, it's sufficiently large so that we have got the final answer from n. So the final answer is accept, and therefore we reject it. We reject it, therefore
n will reject itself.
what happened was that this is the code for M. Yeah, this is the code for language L, which is M. And this X was the code itself, which we ended up by rejecting. So here from accept, we concluded reject. And exactly the same argument, if you start from reject, we would get accept. Why? Again, we say, okay, this is the code of how we decided M, decided L, which is the code of M. And we feed M to itself because the running time of N is only linear, is only 10N. It's definitely smaller than N to the 1.5. So after N to the 1.5, we would get this part to be rejected. And because of the reject, we would accept it, which is the exact opposite. So what you have to recall from this proof is, first of all, the high-level idea that the technique is that you define the language which is in between those two. And the way we defined it is very similar to the way we proved the halting theorem. And the only thing I want to say why this is called diagonalization is that if you draw a table, on the left side you have programs, on the right side you have input. So inputs define the column, the rows define the program, and here I would write what happens if you run this program over that input. So think of a huge table. The rows are the all the programs, all possible programs. This is like infinite table. What we are doing is that we are defining some language or some program or something that, let's call it M. Then we are going to use M both as input and as program and input. And then we will look what happens here. And then we will show that this point cannot be well defined. It's contradictory. M is not going to well behave on itself. If you say it's going to reject, we would accept. If we get accept, we would get reject. And this point is always on the diagonal of this table. Why is it diagonal? Because we are using the same program on the same input. It's M and M. So the term diagonalization, if you hear it, is basically very abstract intuition about these two proofs, that we are basically using the same thing over itself. We are feeding a program to itself. And in both cases, we get a contradiction. In the halting problem, it was just about accept or reject. In the time hierarchy problem, we run it for a specific number of time, and then we decided accept or reject. Okay, so this is for today. Make sure that you're comfortable with the proof. The proof is important because we might see other versions of the theorem, not just for time. We might talk about different resources. And next time we will see like when this technique is not going to work, which we'll see later.